Thanks, Daud, and a very good afternoon to all of you. So, this is the sweet spot to give a lecture because after having such a heartfelt of lunch, I guess all of you will go to sleep after 5 minutes. So, I will try to say whatever I have to say within first 5 or 10 minutes, and then you can relax and enjoy the talk. So, as Daud said, what we'll mostly be discussing is this broad topic, which is tastes of GR and black holes. So this is the basically the broad purview on which my lectures will be based on. So I have already given the five topics that I wish to cover. I am not sure how much I can cover, but still let me try. So the first topic would be far from horizon because my interest will mostly be in horizon. Yes, sure. I will. This is just for some introductory remark, then I will move over there. No. I understand. Okay. So as I was saying, like the first talk would be on, far from the horizon, and then we'll go closer and closer to the horizon. Like suppose you have a distant relative whom you have never seen in your life, but you have heard the descriptions about him or her, and suppose you want to go to meet her from a large distance. You will sort of see, oh yes, I do remember that this person used to have, hand waving like that, movement like that, and it might be that person, and then you go closer and closer, and then you try to understand, yes, this is actually the person that I am looking for. We'll do the similar things for black holes, and as a consequence we'll also try to understand the theory of gravity in the process. Now, as I mentioned, the talk can broadly be divided into two cases. One in which we will try to describe the theory of gravity itself, which is described by the action, is the starting point of all, which you can think as the standard model of gravity, which is d4x root minus g times the Ricci scalar. So I will assume that this is known to all of you before I start. So the argument that it should be Ricci scalar can again be arrived at from various consideration. You might have gone through all of them, but nonetheless I will repeat it once. So normally when you try to construct an action, take a point particle, it is a half q dot square minus the potential, right? And q dot square is the kinetic energy. So now if you have go to field theory, like for example scalar theory, then you would write del mu phi with a proper sign to take care of your signature convention, such that when you decompose it into space and time, you get phi dot square as a positive quantity in your action. So for gravity also, you should have thought that since gravity is described by what is called a metric, then it should be first derivative of the metric and square of it. I mean, as usual for electromagnetism, for scalar, we always have first derivative of the dynamical variable and then squaring it, correct? But for gravity that actually fails because of the equivalence principle, since we know that first derivative of the metric can always be set to 0, because you can go to a locally freely falling frame of reference and there is no first derivative of metric, or in other words the Christoffel symbol can always be set to 0. On the other hand, the second derivative of the metric can never be set to 0, and that is what is responsible for the real gravitational physics that we have here. So given that you construct the Ricci scalar, which has double derivative of the metric, as you know, because the Riemann comes from double derivative of the metric, as it is dependent on first derivative of the Christoffel symbol. So therefore the R is in general a function of the metric, first derivative of metric, and as well as the second derivative of the metric, right? That is something that we know, but this is again a peculiar form of the action, because when you write down the action for a point particle or the action for scalar field theory or electromagnetic field theory, you never had like for example q double dot in your action, or maybe phi double dot in your action, or double derivative of the vector potential in your action. So in that respect, gravity is slightly weird because it depends on double derivative of the metric. And if you have double derivative of the dynamical variable, there are many issues that arises out of it. I mean, I will not go into details because that is not the topic I want to cover, which are known as Ostrogradsky instability. So if you want, you can look it up or we can discuss it at a later stage. But those are not going to affect my gravitational Lagrangian because this term is linear. And due to this fact that this is linear, you can decompose the Einstein-Hilbert action into a part which is quadratic in the first derivative and a total derivative piece. And as a consequence, the field equations and everything follows. There is no issue with the Ostrogradsky instability and so on and so. So if you vary this particular action, and as you know, in gravity or in any field theory in all of physics, the idea is to have one rule to rule them all, like one ring to rule them all. Lord of the Rings, I guess you may have seen, or if you have not, you should watch it. So similarly, there is only one rule, which is you have an action and you vary that action, extremize that action, and that gives you everything that you want. So after variation, you get your field equations, and from that field equation, you can get whatever you want, like you can predict what is going to happen in the future. So the job of a physicist is just like an astrologer, predict the future given some initial date. We are also going to do exactly the same. So the equation that you get from this action is our famous Einstein's equation. So here you will of course get G mu nu equal to 0 because I have not added any matter term to this action. If you add some matter Lagrangian, so which would be something like d4x root minus g L matter, then you will get, instead of 0, you will have nu equal T mu nu, and this T mu nu you know how to derive from this Lm. You just take a variation. So T mu nu would be 2 by root minus g delta of root minus g Lm by delta of g mu nu. So this will give you the corresponding expression for T mu nu, and you can put in whatever your favorite matter Lagrangian, be it scalar, electromagnetism or whatever, and you would get the corresponding T mu nu out of it. Your job is to solve this equation and obtain solutions for the metric G. Right? That's what people who are working in gravity does. I mean, earlier they used to do that. Given this, you choose your favorite T mu nu, plug that in, solve it and get a metric. Now you will realize that this is not a very easy problem to solve in, because that G mu nu is a nonlinear function and so on and so forth. So solving this equation is not very easy. In the context of cosmology, where you have many symmetries to be present, then you can solve it. There can be infinitely many solutions depending on your equation of state parameters. But for the case of static and spherical symmetry configuration, which is our interest, there would be very few solutions that we will be discussing. And in particular, there are only two solutions which is of interest to us. One is the Schwarzschild solution and the other one is the Kerr solution. Now the Schwarzschild describes any spherically symmetric object, for example the metric outside Earth, the metric outside Sun, metric outside any neutron star, outside any white dwarf, most of them which are not rotating, and you can think of them to be static and spherically symmetric. Everything is described by the Schwarzschild metric alone. But now if you have rotation, then the problem is you do have a metric which is the Kerr metric, but that can only be used to describe a black hole, because you do not have an interior solution associated with the metric. So how does it go? So you have, say for example, Sun, and you want to find out what is the metric associated with it. Then outside Sun there is no T mu nu because it's a vacuum geometry. So there you just put T mu nu equal to 0 and solve for capital G mu nu equal to 0, giving you Schwarzschild metric. While inside the Sun there is a T mu nu because Sun is made out of matter, and then you solve the corresponding Einstein's equation inside the Sun, match these two at the surface of the Sun, and as a consequence you get the full metric of the space. The problem is that for the case of rotating, there is no such matching that exists between Kerr metric and the metric inside a rotating star, and as a consequence Kerr metric can only be used to describe a black hole, not a star. So therefore, for the purpose of this talk and for the simplicity, we will restrict to static and spherically symmetric configuration, because that will drive most of the points home. There would be a few issues which I may not be able to discuss, which are very specific to Kerr, but again that you can learn up later, or maybe when Daud arranges the next school, then I will be here discussing the Kerr metric with you. So, for the purpose of this talk then we have the Schwarzschild solution, and as you know that this solution as described by the following line element, which is 1 minus 2 gm by r dt square plus dr square plus r square d omega square, right, where capital M is the mass of the object and d omega square is d theta square plus sine square theta d phi square, which is the line element on the two spheres. So, this is pretty well known, I guess, to all of you. Now, next thing is at r equal to 2 gm or r equal to 2m, because if you put g equal to 1, that is the unit people often works with, you seem to see there is some issue which is associated with it because the metric elements diverge. But then you realize that it is not really the metric that you should be concerned about, but of the curvature, because as I mentioned, due to equivalence principle you can always make a metric locally flat. So, it is not the metric which really carries the real gravity, it is the curvature tensor which does. So, you compute the curvature tensor and a scalar out of it, which is known as the Kretschmann scalar, and you found that at r equal to 2m or 2gm there is no weird physics which is going on, everything is regular except at r equal to 0, and therefore r equal to 2gm is what you refer to as the event horizon. So, there is a reason for that. I will just tell you one reason, there are a few others. So, the reason is the following. So, suppose you take this surface which is r equal to constant, right, this is a surface. Now, I ask you what is the normal vector to this surface, right. So, how do you obtain normal vector to this surface? It is very simple. The normal vector is simply the gradient of r, right. You have a r constant surface, you are going normal to it. So, how do? You apply grad alpha on r and that gives you the vector which is normal to r equal to constant surface, correct. Now, I ask you to find what is the norm of this vector. Can you tell me what is the norm? See, every vector has a norm, right, by definition. So, what is the norm of this vector? Yes, inverse of RR component, correct. So, this should be G upper RR, which corresponds to, right. Why it is so? Because n alpha is G alpha beta n alpha n beta, and only the R component of n alpha is non-zero. So, it will be G upper RR. G lower RR is 1 by 1 minus 2 gm by R. So, G upper RR should be 1 minus 2 gm by R. And as you see at R equal to 2 gm, this quantity identically vanishes. And when the norm of a vector vanishes, then what happens? Null vector, right. So, that is something that we know from our special relativity days, that this is a null vector. So, that means this surface R equal to 2 gm is actually a null surface because the norm of the normal vanishes on that particular surface. Now, this surface is also special from another perspective, is because this particular metric has a certain symmetry which is called the Killing symmetry. There are two Killing symmetries because the metric does not depend on the time coordinate t, neither it depends on the angular coordinate phi, right. So, the independent of t tells you that there is a time Killing vector field which is del del t, or if you want to write it in components, it will be 100. Now, if you compute the norm of this vector as well, and you can actually show that this norm will also vanish when r is equal to 2 gm by exactly the same logic, and at the same time this vector xi alpha will actually map to this n alpha by some coordinate redefinition. So, then what it means? So, after all this dust settles down, is that at r equal to 2m is a null surface because its normal on that surface vanishes. At the same time, the Killing vector is also null on that particular hypersurface, because the norm of the killing vector also vanishes. So that means that surface is not only null, but also on that surface the time-like killing vector norm is also 0, and that tells you that this surface r equal to 2 gm is a killing horizon. That is a very special surface with which event horizon, after there are some causality conditions, some asymptotic condition and so on and so forth, which we will not get into, but r equal to 2 gm is a special surface. So therefore all of our concern will be on r equal to 2 gm and what happens surrounding it. But as I said, when you try to identify some person, you first try to look at it from a large distance and see if you can identify even from there. So here also we will try the same, that what happens when you are looking at an object which from far away. So that would be called the weak field tests of gravity, because there you may not be able to say whether it is a sun or neutron star or a black hole, but at least you should be able to tell whether the space time is described by this metric or not. Now if the space time is not described by this metric, then there can be two possibilities. One possibility is that I have a non-zero value of T mu nu, because as I already mentioned, this metric arises from setting T mu nu equal to 0. So if T mu nu is not equal to 0, this will no longer be a solution of my Einstein's equation. Or the second possibility is Einstein equation itself is not true. Correct? So this is again from Sherlock Holmes. I mean, if something looks very improbable, but if it is true, then that is the only option that you have. So similarly here, I mean, if you see that this metric is not agreeing with your experiment, then you have to argue that either my equation is not correct or I have some T mu nu. But T mu nu you can argue from other observation whether indeed there is some matter which is present over there, and suppose there is none, then the only option for you is to abandon this equation, which means you have to abandon this particular action and go for some modified action which is not just given by R. So that is where the modified theories of gravity comes into play, that is R is just one particular choice, and who tells you that it has to be R. So suppose I work with R plus R square, that also satisfy all the requirements. It is a scalar quantity, it is constructed out of metric and so on and so forth. Suppose I start with R alpha beta, R alpha beta, that is also fine. I mean, it's also a scalar quantity constructed out of well behaved quantities, so there is no issue. Then I can also have terms like R alpha beta mu nu, R alpha beta mu nu, which is also a well behaved quantity, there is no issue. But the equations are very different. If the equations are very different, solutions are going to be different, and if the solutions are different, as you know, the physics is going to be different. So the idea is to propose tests by which you can identify whether your solution is given by Schwarzschild or not. There is one caveat though, there can be some theories for which Schwarzschild is also a solution. For example, if you look at R plus R square theory, then Schwarzschild is also a solution of that particular theory. So by just saying whether it is Schwarzschild or not, you may not be able to kill all the alternatives, but at least some alternatives can be ruled out. For example, if you have R alpha beta or this kind of terms, you can get some non-trivial solution, then you can show that the solution will no longer be Schwarzschild. So therefore, how the game is being played is the following. You propose some test, like let us look at this particular object. One example would be perihelion precession of Mercury, other example would be bending of light. I will come back to it in a moment. Now suppose you are looking at bending of light, which is a very famous experiment that Eddington in 1919 and observed that there is indeed bending of light near our sun, right? So you are asking that bending of light means it is connected to some metric, because the bending of light can happen in Newtonian theory, but that has a value which is half compared to that of GR. All of this will derive, but let us go with the flow for the moment being. So then you can identify, well, this is my bending of light. Now you know what is the mass of your sun from other independent measurement. So you plug that in and check whether values match. If they match, then you say, well, that means really it is a Schwarzschild metric. And if it does not match, then you say, well, then it is no longer a Schwarzschild metric, because I know what is my prediction from Schwarzschild. It does not match with what I have observed. And if it does not match, then you should look for some other theories of gravity where it can match, and there would be some parameters coming from these other theories, and you will be able to constrain those parameters. Your experiment will always have errors. This is not just a number. It means you will be able to constrain additional parameter coming from the other theories of gravity. And that would be the prime focus of the tests of GR, where you try to constrain various theories by studying what are the various black hole solutions they predict, what are their difference from the Schwarzschild if we are just restricting to static and spherical symmetric case, and then checking them against various observations that we already have, right. Then the other set of tests would correspond to whether we are really looking at a black hole or not, but that will come back in the next lecture when we are going closer to that of a black hole. So for this discussion will just restrict to the case of this particular metric, and I will also discuss an alternative metric and various tests of GR. Okay. So any question up to this point? Everything is clear, understood? Okay. So let us now move forward. Okay. So next thing would be to find out trajectory. Okay. Because that is something which is there, like orbits of particles, orbits of stars, orbit of planets, and these are something that we can observe and verify. So for example, one of the Nobel Prize recently went to the motion of a star around our galaxy in our Milky Way, Sagittarius A star, and by observing its motion for 12 years, you can actually sort of predict what is going to be the trajectory of the star, and that you can use in turn to test your theories of gravity. The same that people use for Mercury, for example, or bending of light. These are all the different faces of the same coin. So for trajectory, the first thing, as I said, for the gravitational field you had the action, which is Einstein-Hilbert action. Here also for trajectory you need some action or some Lagrangian to start with. Okay. So we will start with this particular Lagrangian, which is m by 2 dx mu d tau. I mean, this is pretty obvious because for free particle I had half m x dot square. So here also I have half m x dot square, but the only difference is now I have mu nu indices rather than just dot. That gives me this particular Lagrangian. Okay. There is an alternative Lagrangian also, but if a time permits I will come back to it, but this should suffice for our purpose. Now you know what is your G mu nu. So let me, okay, there is one thing which I should mention. So for our purpose I will work with this choice for my metric, so that at the end all the results can be generalized. So for Schwarzschild my f and g are same and is equal to 1 minus 2 gm by r, but in general there is no reason for these two to be identical. There can be metric for which f and g are not same. So the results I will derive for them to be different, but then depending on your case of interest you can put f equal to g and get the results that you want. But so in this way this would be the most general static and spherically symmetric metric that you will encounter. Then you plug this in back here, so you get m by 2 minus f of r t dot square plus r dot square by g of r plus r square theta dot square plus r square sine square theta phi dot square. And this immediately follows because you know what is your metric. Correct? Fine? Everyone? Makes sense? I mean, very good. Now given Lagrangian, what do? You find out the equation of motion, Lagrange's equation. So before you find Lagrange's equation, you always look for conserved quantities. Correct? And how do you determine conserved quantities? That is, if Lagrangian does not explicitly depend on some coordinate, then the corresponding conjugate momenta must be conserved. This Lagrangian does not depend on t, neither it depends on phi. That means the momenta conjugate to t and momenta conjugate to phi must be conserved. So therefore pt, which should be del L del t dot, and that from here is given by minus m fr into t dot. This must be conserved and we define this as m into e. So here m is the mass of the particle. And in relativity, people generally defines energy as per unit mass, so that the mass of the particle gets factored out and you do not have to worry about it. Since mass is a invariant quantity, energy is a constant, m times e is also a constant. So this is the first equation. Right? Makes sense, everyone? Okay. Then you have p phi, and that would be given by from here m r square sine square theta phi dot. Correct? And this is also conserved. So this would be m times L, where L is referred to as the angular momentum. So given these two, you can immediately obtain the following two relations. One is T dot is E by F of R, and phi dot is equal to L by R square sine square theta. Right, everybody? Fine? Okay, good. But now this theta is something which people normally get away with. I will tell you how it can be done. So now you have to determine the equation for r and theta. Correct? Because t, you have already fixed what is t dot, you already know what is phi dot. The only two remaining equations are for r and theta. So for theta, the equation would be dd tau of del L del theta dot minus del L del theta equal to 0. Correct? This would be the equation for theta. Right? Lagrange's equation. Only thing is t is replaced by tau, nothing else has changed. Then if you plug this back over here, then you realize that I will just tell you what will this contain. You can find it out later on because this will not be relevant. I will have terms involving theta double dot, then I will have terms involving theta dot, and I will have terms involving sine theta equal to sine theta cos theta actually equal to 0. So I will have an equation of this form. So I will have a theta double dot term, I will have a theta dot term, I will have sine theta cos theta equal to 0. Now you see that suppose I make the particle on the theta equal to pi by 2 plane, right? So if I put theta equal to pi by 2, then my cos theta is going to be 0. If theta is constant, theta dot is 0, that implies theta double dot is also 0. That means if a particle is confined to the theta equal to pi by 2 plane, it cannot move out of the plane. It has to remain in that plane because theta dot and theta double dot are both 0. So that means if a particle is on the theta pi by 2, it will remain on that plane. This is exactly what you had in the Newtonian mechanics. That is, if a particle is moving on a central force field, then the motion must be planar. The same is true here. If the particle is on theta equal to pi by 2 plane, it must remain on the theta equal to pi by 2 plane. And due to spherical symmetry, theta equal to pi by 2 is no special plane because you can rotate the system and any plane can be theta equal to pi by 2. So that means you can always work with theta equal to pi by 2 plane and all motions would be confined to that plane. This will no longer be true if you do it for the case of a Kerr black hole, and a particle can actually escape from the theta pi by 2 plane and so on and so forth. So you have to be careful in the rotating case, right? But for static and spherical symmetric, theta equal to pi by 2 works fine. If you want more rigor, this can be proved using what is called the Carter constant, but let us not get into those details. But just for the people who are interested, you can do it even more rigorously by following the Carter's constant argument, which people routinely use in car. So after you set theta equal to pi by 2, then where did I put my duster? Here. Then you see that this equation is completely redundant, and here also it simply becomes L over R square. So phi dot is right. So your life is simple, and then the last equation is about R, right? What is this equation for? Now that equation I will not write here, you can write it, but that is not what we really want. So rather what people use at this stage is to use this identity, which we all know is p mu equal to minus m square. This is something which is typical. I mean, you know it from your non relativistic physics, or in the sense of special relativity, that p mu is minus m square, which is where m is the mass of the particle. So if you solve it, what do you get? For this case, you get g mu nu, which means minus f of r into pt square plus 1 by gr into pr square plus 1 by r square into p phi square equal to minus m square. There would not be any p theta because p theta is 0, since I have fixed theta to be equal to pi by 2. So there is no p theta here. Now p upper t, we already know what it is because I know what is t dot. Pt is simply m m into t dot. So this means I have f of r m square t dot square plus m square by gr into dr d tau whole square plus r square m square phi dot square equal to minus m. What I have done, I have changed pt to m into t dot. What is momentum? Mass into velocity. So this is mass, this is velocity. Similarly, into dr d tau and phi, which is m into phi dot. Right? So then m square gets cancelled from both sides, and you get an expression for dr d tau whole square, and that is the equation that we are after. So we get dr d tau whole square is equal to g, then I have minus 1 plus fr into t dot. T dot is here, e square by f square, then minus L square by r square. See, what have I done? This g comes from the 1 by g which is sitting over here. Minus 1 comes from the minus m square after all the m square has been cancelled. This, when you take it to the right hand side, become plus f t dot square. So this is plus f and this is t dot square, and minus phi dot is L over r square. So phi dot square is L square over r4. There is a square here which cancels it to give you L square over r square. All in all, if I write it down, so that would be our final expression, which will be here dr d tau whole square equals to g by f into e square minus f into 1 plus r square. So this would be the final expression that we will get, and this quantity is what people refers to as the effective potential. Okay, think of Newtonian. R dot square is equal to E minus V effective. Now instead of E, we just have E square. There is this extra factor of G by F which goes away if G is equal to F, and then this is the effective potential, as simple as that, right? Now this equation can also be derived from a Newtonian point of view. Can you argue how? The same equation with just two small changes. Tell me. That I should cover. Anyone? They just think, see, physics is very simple, you just have to think straight, that's all. So what we have in the Newtonian? Newtonian in the sense relativistic but not Einsteinian gravity, so to speak. So what is my momentum? Momentum is m dx mu d tau. Now theta is constant. So that means I will have m dt d tau. So okay, let us do it for the three components. So I will have dr d tau 0. This is my 3 momentum. If you are too much onto it, you will simply write it as gamma mv, where gamma is what? dt by d tau, the 1 by square root 1 minus v square, that factor. So this is the momentum, right everybody? 3 momentum. Then what is my angular momentum? R cross p, right? Angular momentum is R cross p. So if you take R cross p, this is not going to contribute because this is along the radial direction. So R cross R is 0. So the only term that contributes is this. So you get mr d phi d tau, right? This is R cross p. Now we know that what is E square? E square is m square plus p square, right? I mean C is set to 1, but this is what you get. Now what is p square? P square is m square dr d tau whole square plus m square right? Fine. Now what is d phi d tau? L over mr. So this will become m square 1 plus L square over R square plus m square pardon me? Why m square R square? D phi d tau is L over mr. This one's mod square, right? No, but that actually comes from the angular momentum. See, what happens here is that this R takes care of it. See, it's all the same. Suppose you put here an R into d phi d tau. That's what you are saying. Because of the dimension, this is of R and this is also of R. Okay. Let us see how it goes. Then you will also have an R square here. But at the same time, this will also become R square because your R is going to cut and hit here. So you see, ultimately you will always get 1 plus L square over R square. It does not R or not. Yeah. So that you get 1 plus L square over R square and you get m square into dr d tau. So therefore you can combine this to get dr d tau whole square equal to E square by m square minus. So you see that is very similar. 1 plus L square over R square, then you have a E square. The only thing that is missing is this F and this G. Correct? Now that F and G also I can get you by redshift argument. So energy in one frame is not the same as the other. As you know, there are redshift which is happening, and what you can show is that under redshift this E goes to E over F or E over root F. So this E will scale to E over root F, and this dr is going to scale to dr over root g. Why dr over root g? Because I have dr square over g. So dr over root g effectively gives you sort of an effective length scale with which the metric element becomes 1. So if you make these two changes, you can see it becomes e square over f. You take f common, it becomes f into 1 plus l square over r square. It becomes 1 over g on this side. Take it to the other side, it becomes g over f, which is precisely the equation that I have. But in this whole derivation, except for this root g and root f, which are the redshift factor, and that's where the information for gravity is present, rest of this derivation is purely flat space-time computation. There is no geodesic equation, no metric which has come into play. So that is what I tried to argue, that this particular equation, even though you might think that it is only coming from a GR, this equation can very simply be obtained from a simple-minded special relativistic calculation, where you compute your 3 momentum, compute your 3 angular momentum, and use the simple dispersion relation, and use this fact that you have a redshifted energy and redshifted dr. That is where the information for gravity is present. Not exactly scale factor. See, what you can do is to go to this local inertial frame or go to this non-coordinate basis kind of a thing that people say. So you can say dr by root g is my new radial coordinate. So then you can see this metric is looks like a flat, like d capital R square plus something. Here also dt is redshifted by an amount root f. Now since energy is inversely proportional to that, that's why in energy we'll have 1 over root f which is present, and hence you will get a factor of f out of it. Okay, this was just to illustrate you that complicated general relativity equations can be obtained from simple flat space-time perspective. Right, is that fine? Should I explain any further? It's okay. So I will erase this because I will need this board. Okay, very good. So after having this equation, next thing that I would like to tell you is another way of obtaining this, and which is a more robust way, which is known as the Hamilton-Jacobi method. I will very briefly mention it, but you can work it out of your own. So the Hamilton-Jacobi method actually solves this equation. I mean, this you must have known from your classical mechanics computation. So this is what is known as the Hamilton-Jacobi equation, where A is referred to as the action of the system. So del A by del x mu is nothing but the momenta. Del A by del x nu is also momenta. So this equation is equivalent to saying that p square is equal to minus m square, which is nothing but the relation that we used in order to arrive at here. Now what you do, you expand, you put everything, so you know what is your g mu nu. So this equation will boil down to minus fr into del A by del t whole square plus 1 by fr plus gr into del A by del r whole square, and theta I will anyway take it to be constant, so I will have 1 by r square del A by del phi whole square equal to minus m square. See, g upper tt is minus 1 by f, g upper rr is g, and g upper phi phi is 1 by r square, because theta has been taken to be pi by 2. Now next step in solving this is to take a to b, because it does not depend on time, et plus l phi plus some r of r. This is what you do, and if you substitute this back here, you can see this gives you an e square over f, this gives you an l square over r square with a m, so you should write a over m, and it's exactly the same. So if you put it back here, you will find that dr over dr whole square is equals to 1 over g. Then you have on the other side, m is going to cancel, 1 plus l square over r square with the f, and then f will come here, and then you will have plus e square. See, del A by del T is E, correct? So you will get a E square from here. F I have taken as a common factor, so F will come over here. This will give you L square, because del A by del it is L square over R square, and M you take it to be out because there is already a M over there, so M gets cancelled. So you get 1 plus L square over R square. You get E square divided by F. So F you have taken outside, that means it gets multiplied with F. This becomes G into dr by dr. So you should have a G over here and 1 by F. So modulo this overall factor, you can see the term inside the bracket is same as what we have over there. It's exactly the same on both sides. So this is also another way of obtaining the corresponding equation, and then you can relate this dr over dr smaller to dr over d phi, which I will not go into now because of time constraint, but this would be another way of solving the same equation but from the Hamilton-Jacobi perspective. In particular, if you are doing it for a Kerr black hole, that is the reason I brought this up. This gives you a much faster way of arriving at the relevant equation than going through the Lagrangian, because for Kerr black hole there would be complications in the metric because of cross term. So there this particular decomposition of the action in terms of E into T plus L into phi plus R into R will turn out to be much faster, and that will give you the relevant equations that you are looking for. Fine? Clear everyone? Absolutely. So how the Carter constant comes is that, as you can see, I have ignored the del A by del theta term by saying that I am working on theta equal to pi by 2 plane. If I have not, my final equation will be an equation for R plus an equation for theta. Now you know, whenever you solve like Schrodinger equation, when you solve using separation of variables, you had one part which only depends on R, one part which only depends on theta, then you say that each part is individually equal to a constant. The same is true here. There would be a part which only depends on R, there would be a part which is only dependent on theta, and the separation constant between the two would be given by the Carter constant, and that is important in the context of Kerr black. This, okay, so this is easy because you see, as I mentioned, del A by del T is the momenta which is conjugate to T. That's how we arrived at here, that my T mu is del A by del x mu, correct? So that means del A by del T is Pt. Now what is my del A by del T? Pt, which is m into E, correct? So that means my del A by del T, which is Pt, which is minus me, E is constant, so you can integrate that to get E into T, correct? That is how the whole thing is being done. You can just, I mean, this I have written because I know that the form has to be this, but if you want a formal derivation, it appears from here. Similarly, del A by del phi would be equal to P phi, and I know that P phi is equal to m into L. That means my A would be m into L into phi, right? So that's why I have L into phi and I have a division by L, right? Fine? Yes. You mean this minus sign? Yeah, sure. I mean that is also here, because you see the P T dot we want to be positive, and that is why there is a negative sign which is present. Agreed. But then you see, ultimately it does not matter, because what sits here is square of E. So what you define as negative of E will also give you the same equation. But just to match with the Newtonian context, because there we know what is the definition of energy, and you can also define an energy here in terms of the scaling vector, and just to keep them consistent, the sign is chosen. If you had chosen a metric with this to be plus and this to be minus, then maybe you would choose the opposite sign convention. Right? Makes sense? So where is it? So this is also something that I do not need. The last bit which is remaining is the massless limit, because that we'll be using pretty often. Now massless limit is you may say it is very easy. I will just put m equal to 0 here, but then you realize that your Lagrangian itself vanishes. If you want to find out Hamiltonian, for example, corresponding to this Lagrangian, you will find the Hamiltonian depends on inverse of the mass. So again, then if you put m equal to 0, your Hamiltonian goes for a toss. So then how do you take the massless limit? The easiest way to take the massless limit is again the equation that I have erased. If you remember, the equation was del A del x mu del A del x mu equal to minus m square. So I can easily take m tending to 0 limit and nothing is going to be affected, right? Clear? There is another way which is sort of more rigorous, derive the massless limit. So that goes as follows. So for that you start with an action which is half integral 1 over chi g mu nu dx mu d lambda sorry plus. So what you do, you add this auxiliary field or this additional field chi, which does not have any dynamics, because derivative of chi never appears into your Lagrangian. So in addition to x mu, you are also going to vary this quantity chi, and as a consequence you will get two separate equations of motion, one for x mu and one for chi, and then you take the limit which is m tending to 0. And you can show that that limit actually works pretty well, because this equation is perfectly fine when m goes to 0, m is not multiplied with it, so there is no problem. In some sense, So when you vary this action, what you will get is that a solution would be chi equal to m for the case of massive particle. So if you have massive particle, then you can show that chi equal to m would be the solution, and then what do you get? 1 over m, sorry, chi equal to 1 over m would be the solution. Then you get chi 1 over chi to be m, so you get m by 2 g mu nu x mu dot x nu dot, which is exactly same as the Lagrangian which I have, m over 2 g mu nu x mu dot x mu dot. On the other hand, if you have massless particle, then your chi can be anything. Any constant value serves your purpose, and then the same just goes to 0. But this term does not go to 0, it remains as it is. So let me reiterate. Here you vary this action with respect to x mu and also with respect to chi. There would be two variations, because there are two unknowns, I should have two variations. When I am varying them and setting them to 0, then for the massive case, you will get chi equals to 1 over m. So as I said, if chi is equal to 1 over m, it is very clear that modulo a constant factor, and as you know, to a Lagrangian you can always add a constant, it does not do anything, but this action would be same as this action, because chi is 1 over m. But on the other hand, when you are doing the massless case, then chi cannot be related to mass, it has to be some constant. And if this constant is chosen to be 1 or something, this goes by the name of affine parametrization. Otherwise, it is known as the non-affine parametrization, depending on what constant value that you choose. But there is no issue with the inverse of mass. So this is the formal way of tackling the massless limit. Or if you want a more easier way, then you just put m equal to 0 in the Hamilton-Jacobi equation, you are done. But here in this formulation, you cannot set m equal to 0 here, because then the Lagrangian itself goes to 0 and there is nothing for you to vary. Clear? Makes sense to everybody? Now for the massless case, I will not write it down exactly, I will give it as an exercise to derive. But what you can see is very easy. Can you tell me where this 1 comes from in the derivation? So how we derived it? We take the condition p mu equal to minus m square. that m square give me this 1. So if I put m equal to 0, the only upshot is this 1 will not be present here. So that means for massless particles, so this is massive. For massless particle, the equation will simply be this will be massless. And you can see the main difference is this is f into L square over R square, while it is f into 1 plus L square over R square. Right? So let me see what else I have to do. This is done. This is also done. Very good. Okay. Fine, clear? This. So now I have an expression for dr d tau, and from here I also have an expression for d phi d tau. So if you remember what you did in the context of Keplerian motion, you had equation for dr dt, you had an equation for d phi dt, you eliminate t to obtain an equation for dr d phi, which gives you the orbit. So the same is to be done here also. So I have dr d tau and I have a d phi d tau, which is phi dot. So we want to eliminate tau out of here to get an equation for dr d phi. So let us do that. So we have, so let us do it for the case of massive particle, then we will do it for massless. So dr d tau will be given by okay, let us make it square, g over f and similarly square, that would be given by over R4. Can this, yeah. Sure. Yes, of course. See, this equation tells you, as you said, that this means that I have a particle which is not perturbing my geometry but has a mass. Correct? And on the other case, you have a massless particle which is moving. I would say in both the cases, what matters is the energy, not the mass of the particle, because that is what is relevant. So in the case of massless particle, it also has an energy. The massive particle also has an energy. The energy of the particle is supposed to be much smaller compared to the typical energy of the black hole or the system itself. Like for example, Earth moving around the Sun can be approximated by this equation of a massive particle moving in the geometry of Schwarzschild, where the capital M is given by the mass of the Sun. Similarly, motion of a photon around Earth or in the solar system can be described by this particular equation, where capital M corresponds to the mass of the Sun. Correct? So the energy is small. That is how one is going to interpret. Okay, so then out of this you get this equation, which is dr d phi whole square, by just taking a division of the two, and you will get g over f r4 e over l whole square minus f over l square into 1 plus square. See if it makes sense. Everyone? It's fine. Now instead of r, I mean it is often easier to use inverse of r, which is denoted as u. So this is also true in your Kepler's problem, where also instead of r you use this u variable in order to solve things. And if you plug them in, you will see that this is du d phi whole square, because dr d phi is 1 over u square into du d phi, r is 1 over u, then I am taking square of it, so I will get 1 by u to the power 4 here. This r to the power 4 will also give me a 1 by u to the power 4, so these are going to cancel and you will get g by f into e by l whole square minus f by l square. So this is one of the main equation that we will concentrate on. Fine. Any question? So having obtained this, next step you can work with any choices of g and f and try to solve this equation, right? But in general, as you can anticipate, solution is a bit difficult to obtain, so people use various approximation schemes in order to solve it. So next thing, I will use this equation, but in the context of Schwarzschild geometry, because my main motivation is to study what happens in the context of Schwarzschild. Fine, and then how things can be generalized to the other cases. Is that fine? Clear? If I do it for Schwarzschild, then you see that this equation becomes du d phi whole square. G is equal to f, so the first term does not matter, because for Schwarzschild g, tt and gr are the inverse of each other, so g is equal to f. So I will have e over l whole square minus f is 1 minus 2m u, then you have 1 over l square plus u square, right? I have written what is f, 1 minus 2m by r, which is 1 minus 2m u. L square I have divided 1 plus l square u square, so I will have 1 over l square and just plus u square. So if you break it up further, okay, let us keep it this way. Now the job is to find out trajectory in this space time, and as we know that there are elliptical orbits in the case of Newtonian orbit equation, and here we just assume that we will get some corrections out of it, not all of things. So there will be some correction over and above the Newtonian trajectory coming out due to this particular effect. And if you actually work it out, you will get this equation to be e square minus 1 over l square, then you have plus 2m over l square into u minus u square plus 2m into u cube. So there would be term 1 over l square, which is here, then you have 2m u by l square, then you have this term u square, and then you have 2m u cube. So this is the correction that you have, which is coming from GR. Rest of the terms are there in the Newtonian case also. This is the only term which is contributing from general relativity. So therefore, if you ignore this term, this equation is exactly as in GR. So as you can easily see, this u square comes from the angular momentum barrier, which is L square over r square. This u comes from the 1 by r potential which is present, but there is no way you can have a u cube term into your equation. Right? In Newtonian case, what happens? There is this potential v, and in addition there is an angular momentum barrier. These are the two things that you have. This is your angular momentum barrier and this is your 1 over r potential, but this is the extra piece. Correct? And there is something called Bertrand's theorem, which if you have not heard, you should go back to Goldstein's book and check, which argues that if you have additional terms like this, then the orbits do not close. So that is exactly same in GR, that orbits in GR except for circular orbits, they do not close. And in particular, the orbits would be something like this. So they will come back and then they will start moving around. Okay, so they will never close. In a sense, it will not be a closed orbit, but it will be bound orbit. So it will be bounded between two radius, which are called the perihelion and the aphelion. These are the two radius between which the orbit would be bounded, right? But they will never close, in the sense that it will not be an orbit like this. So that after 2 pi rotation, it comes back to its initial value, and that is precisely we want to find out, that after a 2 pi rotation, which value does it come back to, correct? That is the main point of this. Fine. Any question? Sorry. Is it? No, actually we do not get this equation. If you remember, with special relativistic argument, there are two things that we did not get. One was this f we could not get. It was simply e square minus 1 plus L square over R square, and this g we could not get. This g and f come by introducing the gravitational redshift, for example, and which is a purely general relativistic effect. The special relativity will tell you that it is e square minus 1 plus L square over R square. Then if you recall, I said E goes to E divided by root f. That is a general relativistic statement, and dr going to dr by root g, which is also a general relativistic statement. So only then you get back this f and this. So now we have to solve this equation. So there are many ways actually to solve it. So there would be there are mostly two main ways that people use. One is you take another derivative of this, so we will get an equation which is d2u by d phi 2. This u square will give you a u. So therefore your equation would be something like this: d2u d phi 2 plus u equal to f of u. Now this equation, you know what is the solution? This will be some cosine of phi, and that will correspond to your circular orbit or elliptical orbit, because in polar coordinate your elliptical orbit's equation is 1 by r equal to cos phi with some initial parameters. Then this f of u is going to do modifications on top of that. So you have to compute this modification and find out how things are going to behave. Rather, I will take a different approach because it gives you result which can be generalized to many other cases. So the approach is as follows. So you know, as I said, this orbit has a perihelion and an aphelion. So this corresponds to that the particle is going it and then comes back, right? That's what happens at the largest distance and also at the smallest distance. So at these two radii, which are denoted as UA and UP, corresponding to perihelion and aphelion, the du d phi must vanish. Because at that point the particle is instantaneously, there is no velocity, but then it comes back because of the gravitational force. This is just like a harmonic oscillator. Think of a pendulum which is oscillating. At the end points it does not have kinetic energy, it just have potential energy, while at this point it is fully determined by kinetic energy and no potential energy. The same is here. The two endpoints of your simple harmonic oscillator is in this case like the perihelion and the aphelion, where there is no du defined, I mean there is no velocity, so to speak, there is only potential energy which is present. So du d phi must be 0 at both of these 2 points. Then you substitute it back here and we want to solve for energy and angular momentum out of it, right? That is the next aim. So then you see you have two equations. One is e square minus 1 by L square plus 2m by L square UA square into 1 minus 2m UA is 0, and the other equation is UP see if you agree. So both of these equations must be satisfied. Right? Fine. Now you can easily find out what is E and L from here. Determining L is the easiest, which is you simply subtract these two equations. So you see that the contribution coming from the energy cancels out right away. You only have contribution from the L square. So you get 2m UA minus UP divided by L square, that is equal to, I am subtracting, so this would be plus, this would be minus UA square UP, and that tells me that 1 by L square should be so this would be my 1 by L square. Right, and this is just your standard algebraic equation, two variables, and you have to solve it. After obtaining 1 by L square, you can plug that back into any one of this equation and determine what is your energy in terms of UA, UP and mass of the particle. Fine, here. Okay. Next step of this is to rewrite this equation as d phi du, that is equal to 1 by square root plus u square, which means I can take this outside. So I will have to the minus half square root E by L whole square 1 by 1 minus 2 mu minus. So this is what we will have. What I have done is simple. 1 minus 2 mu I have taken outside the square root, so it becomes minus half, and then it becomes E by L whole square 1 minus 2 mu and u square plus 1 by L square. That's all that I have done. Okay, nothing else has been done. The approximation, because as I said, you cannot get an exact general solution, you have to do some approximation. The approximation is m into u is a small number. Why so? Because the typical, so m is a mass scale, right? That you can convert to a length scale by taking this combination. So g m over c square you can check has a dimension of length. So any mass you can convert to length by simply multiplying by g and dividing by c square. So for sun, for example, the typical radius gm by c square corresponds to 2 kilometer. On the other hand, the u, which where it is located, is astronomical unit away. So m into u, or in other words gm by c square into u, is a very tiny number of the order of 10 to the minus 10 or even smaller. So that means I can always expand my results in powers of g square. Where I cannot do that? I cannot do that if my orbit is closer to this gm by c square radius. But for sun that is never possible, because the radius of sun is much larger than gm by c square. So therefore this condition for sun at least is always true, that Gm by c square into u is much smaller compared to 1. If I do that assumption, then I can do a Taylor series expansion over there. I can also do a Taylor series expansion over there. That means the term inside the square root is a quadratic function of u, because this, if you expand, will give you a linear term in u. There is a u, this would be a quadratic function of u. So this tells me that I can rewrite it as 1 plus mu divided by square root of c u minus ua up minus u. Because I know that at u equal to ua and u equal to up, inverse of this quantity vanishes, because that is the condition that we have here. So that it must be factorizable into this form, and this constant c I need to determine. Correct? Fine? Yes. Yes. G and C is 1, that means m itself corresponds to a length. So m into u is dimensionless, because u is inverse of length and m is dimension of length. So mu is a dimensionless quantity. Fine? So is this okay? Next thing is to see what is this constant c over there, and how do you determine this c? By taking the asymptotic limit, which is u tending to 0. U is 1 over r. I don't know if I have erased it. No, there. So that means r tending to infinity implies u tends to 0. Correct? Yes. Inverse length, which is from there, which is same as inverse of mass, because mass is same as length in the unit system that we are considering. You see, there are two distinct units that physics use. One is c equal to h bar equal to 1, in which case mass and length are inversely related, and the other one is g equal to c equal to 1. There is no h bar equal to 1 assumed here, because we are doing purely classical physics. So in which case you have mass is equal to length. So these are the two different unit system. One is used by particle physicists, the other one is used mostly by people doing things in gravity. Now what I said is that the term inside this square root is written like this. Now if I take the limit where u tends to 0, then what do I get from this side? This gives me e by l whole square, then minus 1 by l square, right, when u goes to 0. Correct? On this side what I get is c into ua up with a minus sign, and that determines for me what is c. My c is 1 minus e square ua. So this is my choice for c. Not sure. So this quantity inside square root has been written like this. Why? Because this is also quadratic in u, this is also quadratic in u. Now I am saying there is a constant c which does not depend on u. So that means its value for u equal as its so therefore I take the limit where u goes to 0. So when u goes to 0, this function is minus ua into up. So it is minus c into ua into up. And this function when u goes to 0 is e by l whole square minus 1 by l square. So that determines for us the quantity c. Right? Okay. Now you have c which is determined, and then you have ua and up. So the next last step is to do this integration, so that you can determine your phi minus phi 0, which is integral du 1 plus mu divided by square root of c so this is the integration that you have to do. So to do this integration, you have to do a substitution. I will just write it for you. This is a tricky substitution which I do not remember. So the substitution is the following: U equal to UP by 2 plus so this is the substitution that you do. And if you do this substitution, then you can see what happens when you compute U minus UA and UP minus U. This will give you sine and this will give you cosine, so that you effectively get okay, let me do it here. So you see U minus UA, if you do, it will give you UP minus UA by 2 plus, right, everyone? That means I can write it as 1 plus sine phi. Similarly, the other one will give you 1 minus sine phi. So when you multiply the two, you will get 1 minus sine square phi, which is cos square phi and a square root. So you will get 1 by cos phi, and du is nothing but cos phi d phi with some initial factor. So that cos phi and cos phi cancels from both sides. There would only be a sine phi coming from this integration, which you can easily perform, integration of sine theta d theta. And after you have done this integration, substituting that value of C, remember that C depends on E and L. For that you have to substitute this choice of L that we have obtained, right, in terms of UA and UB. The final answer that you will get would be 3 pi m. So this is the final result that you will get. See, the steps I am not doing because those steps you can work out. I am telling you what is exactly the transformation, and everything is there. I mean, this is a very simple elementary integral that you can perform, and you know what is C in terms of E and L, you know what is L in terms of UA and UB, you also know what is E in terms of UA and UB by solving these two equations, and the final result that you will get. And you can show in addition that this is same as 6 pi m by L square. I think that is correct. Let me see. Yes, it should be a square by L square. This is dimensionless because UA plus UB has a dimensions of inverse length and this m is length, so therefore this is dimensionless. This is also dimensionless because angular momentum has the same dimension of length, as you can show. So this would be a dimensionless combination that you will get. And this is the result that you will find in all the textbook regarding the perihelion precession of Mercury, which is 6 pi m square divided by L square with this 6, right? Yes. UA plus, yeah, sure. Now comes the next part, that is how to test for GR. Okay, so I will give you one example. So the example is simple. Suppose instead here you have F equal to G okay, and now many might be familiar with this Q because this is known as the Reisner-Nordstrom metric, which corresponds to the electrically charged black hole, where along with mass your black hole also has an electric charge. But it turns out that the solution is not just restricted to that of an electrically charged black hole. If you consider a black hole in a class of modified gravity theories, which are known as the Horn-Deskey theories, these are the most general scalar tensor theory that you can write. People have found some black hole solutions in those theories as well, and those solutions also resemble a very similar metric element, which is this, where this Q now does not have an interpretation of an electromagnetic charge, but rather as an interpretation as a scalar here. In the sense, the scalar field does die down at infinity as 1 over r terms with the scalar field whose coefficient is q. So that's why this q is called the scalar charge. Also, if you look at higher dimensional theories, because as you know, there is a consistent literature where people argue that our universe is not 4-dimensional, but rather there can be some hidden spatial dimension which is present. These are known as the extra dimensional models of our universe, in which case also if you try to solve the field equations which are different from Einstein's equation, you will get exactly this solution. So that means this solution can actually act as a proxy for many things. If my Q is positive, then it always tells you that this is either a Raisman-Nordström black hole or maybe a scalar charged black hole. But if Q is negative, then it can actually come from an extra dimensional black hole as well. So depending on the sign of Q, you can distinguish between 4D black holes, higher D black holes. If Q is 0, that means it is only Schwarzschild. If Q is non-zero, that can mean it is coming from some theories beyond GR and so on and so forth. Then you can redo all of this analysis for this metric, because you know what is your F, you know what is your G. The only thing that changes is here, instead of 1 minus 2m u, you will have an extra term which is q times u square, correct? And then you have an extra term which is also here u square, so that means you will have an extra piece here which is of order u to the power 4. The same argument goes through, you will have ua and up, you can play exactly the same game, and in which case if you compute this integral, you can do that, I am assuring you of that, then your delta phi will turn out to be something like this, 1 plus 4q. So when you put q equal to 0, you get back what you had for Schwarzschild, which is 6 pi m square over L square. For q being positive, you have a precision which is larger than that of Schwarzschild. If q is negative, you have a precision which is smaller than that of Schwarzschild. So that means, suppose at some day you could see some star and some orbit which is, some compact object and orbit of a star or planet around it, and you see that by knowing the mass of the object, you can, and you know what is UA and UB from your observation, like what is the location of the perihelion, what is the location of the aphelion. So you know what is UA and UP, you know the mass of the object from some other independent measurement. Then you know what is your prediction from a Schwarzschild black hole only, which is 6 pi or 3 pi m into UA plus UP. Then you also know what is your prediction for this particular case with a charge q. If you see that your measurement is not matching with the Schwarzschild value, that actually means that you should have a signature for q. If it is larger, then you will say q is positive, which can mean it is Raisman-Nordström and so on and so forth. If you say the amount is smaller, you will say q is negative, which can mean this has some extra dimensional origin. So this is one of the way in which you are going to test your theories of gravity. So this is one observable, one measurement. You can measure it for different systems, come up with different numbers. You know what is your prediction from your theory. You just match it with your data and compute what happens to the Q. Now normally you cannot say that it is beyond GR, because you have to do some statistical analysis and you have to say with it with some significance. And all the cases that we have seen, like that of Mercury or the S2 stars, everywhere GR is consistent with the observation. And then what you can do, you can put bounds on Q, because your observation will tell you, for example, delta phi has some value, say 40 micro arc second or something, then you have plus minus 3 micro arc second. So this is your delta phi. So you have measured it not exactly as 40, but it has some errors which is present. Now if you indeed has some modified theories of gravity, which means you have some non-zero choices of q, then it must be present within this bound, because if q is so large that it takes your delta phi to be larger than this bound, then it is no longer consistent with your measurement. So then in turn you can put some constraint on your q, that my q has to be between say 0.02 to 0.03, only then I will be able to satisfy this particular constraint. So even if you cannot say whether it is beyond GR theories or not, you can at least put some important constraint on this q. And this has been one of the prime focus research area in all of gravitational physics. That is, you look for various observables and try to find out what are the bounds on the corresponding quantities coming from theories beyond GR, and see if two of them are consistent. In the sense, suppose you have some other observation, say bending of light, which I will discuss in the next class. So there suppose you find a bound of q which is not consistent with the bound that you get from perihelion precision, then that will immediately tell you that there is some issue with this particular model, because from two different observations you are getting inconsistent bounds, and then this theory can be ruled out. So that is how you can progress. You use more and more observable, use more and more data, and try to find out constraints and see if these are actually consistent with each other or not. And as I said, this is a weak field test of GR, because while coming from that square root over there to this, I have assumed that m into u is a small quantity, is smaller than, much smaller than 1. And that, as I argued, is only true if this u is very small, or because u is 1 by r, it means r is very large. So I am far away from that object. When I go closer to the object, I will see a very different picture, and that is what we will do in the next class. So I will stop here. So what I have done is to discuss things with massive particle. The massless case I will take up in the next talk, and there we will discuss the photon sphere, and depending on time permitting, I will also discuss the quasi-normal modes of black holes, and then we will see what can be done. So yeah, any questions? Yeah, I have written it q just to keep everything like, in the sense q can be negative as well in the extra dimensional models. So even, I mean, this sign itself can be negative, so it did not be. Then correct. So if q is electric charge, then this is always a positive definite quantity, and also for a scalar here. So for scalar here, if I remember, people generally have phi to be q over r. No, yeah, so the limit I think was something like mod of q was less than, I think, 0.04 or something, which is not very strong, I would say, because the mass of the black hole can be pretty high. So therefore this is a very strong bound, but there would be other ways of constraining it. As of now, I think you cannot go much better than that, because if you, even if you do it for q and m, which I will discuss, even then you cannot get better bounds, because we have much less signal to noise at that particular point. But in future, hopefully we will be able to do it even better. Sorry. Anything else? Yes. Yes, done. Yes. Yes, yes, yeah, Foucault's pendulum. Correct. Sure, of course, because you see that Foucault's pendulum, I'm not sure if all of you are familiar with it. So you sort of solve the Lagrange's equation in a rotating frame of reference, and as a consequence, you have the velocity dependent potential which arises due to the Coriolis force, and then there is a centrifugal force which gives you this omega square r square kind of a term. and then if you solve it, you will find that the orbits do not close. It sort of moves along and it changes its plane of motion, and that actually people used to argue what is the period of Earth's rotation along its own axis, because it is related to that. So as to answer your question, these two are related because that means you are going to a non-inertial frame of reference, and that causes this particular effect. Here also in the context of gravity, when you are looking at a frame where gravity is present, it is effectively non-inertial because acceleration can mimic gravitational force to some extent. So therefore, in that analogy, you can think that non-closing of orbits can be related to the Foucault's pendulum, because this is also a non-inertial or accelerated frame of reference in some perspective. But it does not answer it fully, because you see, even if you have Newtonian gravity, then also you have a gravitational force which is non-inertial, but there you had closed orbits. But it is just because this m into u cube correction, it becomes, I would say this is more of an analogy, that in both the cases non-inertial frame lead to non-closedness of orbit, but a direct correspondence may be a little trickier to obtain. But yeah, I mean there is that analogy over there.